right, excellent. All right, I'd like to start by saying how happy I am to be here. I've been to, I think, nearly all of these conferences from the beginning. I remember when Lou Elizondo was here on that first night. And today I'm going to be talking to you tonight about the latest scientific news from the University at Albany and from UAPx. We have a very fruitful collaboration between UAPx, which is a nonprofit, and the University at Albany. So I'll be talking about not just my own work, I'm the speaker, but this is a team effort with Kevin Knuth, who gave a talk earlier, with our colleague Cecilia Levy, and we also have Ben Kugelski. We have Matt Phelan, who's here. He's hiding here somewhere. And Gary Varese, our fearless leader. And so the first thing I want to talk to you about is, of course, the team. I just mentioned several members, but we also have, I mentioned some of the board members, but we have Rich Hoffman, who is also essentially our liaison with the SCU. We have Candy and Ralph Seeger, who are here in the audience as well. Electrical engineers who are also SCU members. I put asterisk people who are also SCU members, who have been instrumental in our instrumented efforts. So I'm a dad, so I get to say dad jokes. I'm allowed to. So we do have this documentary, A Tear in the Sky, that I suggest you check out, and Travis Taylor was in it as well. So what are the objectives of UAPx? How is our mission different from other organizations? Well, we want to acquire data that fills in the gap on the scientific knowledge of UAP, stemming from a lack of high-quality, unclassified data. We want to make said data, as well as analysis results, publicly available once we have completed our own analyses. We also want to combine existing hardware in new ways, as well as develop new sensors as needed in order to accomplish these objectives. We do not analyze or reanalyze historical UAP cases. That's not to say we're not discounting them, not at all. They're extremely valuable. And as you'll see, it's because of many historical cases, and not just famous ones, but the whole body of cases motivates our choices of sensor technology. So the reason why we don't do analysis of historical cases, because you already have groups that are doing that. SCU does that and publishes monographs on their results. We already have organizations that are doing that. So we have different objectives that are complementary to existing organizations like SCU, but we work hand in hand. So we have this preliminary paper. It's not through peer review yet, but it's on a website that many physicists and other scientists use called the archive, where you can put in the preliminary so-called preprint version of a paper up. And we have this initial results from the first field expedition of UAPx. And even though this was not through peer review yet, which we're still working on, this we consider still a pretty important milestone. Because if you're not familiar with the archive, arxiv.org, it's not a journal, so it's not peer reviewed, but unfortunately sometimes it sort of acts as a shadow journal. And you can get rejected from being allowed to post even without review. And this has happened to people I know in this room or on Hoover on the conference. And it's also it can be kind of random who's moderating, that day or that week. So we were blessed by the archive gods, and we got our paper up there. And that should be a pretty big milestone. Media interest, almost none. Should have been huge. If Kevin and I and Cecilia were at a big name institution, would have been splashed all over the New York Times even before peer review. So perhaps it's a blessing, because we will try again to get people to care. In the mainstream media, although as Ross said, who cares about the mainstream media, said last night, but we didn't get anybody to care or write up the fact that we had made this post to archive. I personally emailed like 40, 50 people, but it might be a mixed blessing because we'll try again after it's actually published and getting different media outlets interested in covering our paper. And the other thing is, you'll see in my talk today, we might have been too humble, too boring. We don't make any bold claims of any smoking gun, which, as Kevin told you earlier today, is really unlikely in most scientific disciplines. You look at the history of science. We don't have some magical smoking gun. We don't have a photo of aliens waving from the window of the mothership. But what we have is a serious attempt to take data ourselves, non-classified data being taken by civilian scientists and engineers and citizen scientists. So what is the ideal method we strive for? So here's a quote from a very famous individual, Galileo. Measure what is measurable and make measurable what is not so. So we can break up our ideal method, and I call it ideal because we did not succeed on all 4 of these bullet points in our first expedition to an alleged hotspot and trying to get data. We didn't succeed in all 4 of these. This is the ideal that we strive for. So we want to commission multiple cameras and multiple copies of other sensors to capture something from different angles at high resolution. That way, if we see the same object or phenomenon in 2, 3, or more cameras and non-cameras, other types of sensors, that's going to allow for robust estimations of distance, size, speed, and acceleration. We also are looking at coincidence timing across all of the different sensors, because that will reduce the amount of data you have to go through by helping you identify what could be ambiguous and what could be a true anomaly. Number 3, we want eventual construction, and many people have the same idea, and we should all work together. Construct permanent or semi-permanent stations that use automated remote sensor suites to serve as near continuous data collection stations. We would need to do so in both control areas as well as supposed UAP hotspots. And that is a key difference also. We've talked about setting up stations in supposed hotspots. We have a twist on that because this is a key part of the scientific method. You know, in drug studies, you have the placebo group. In other scientific disciplines, you have to have control. So we want to have control data in boring areas or areas that we know what the objects are. It's near an airport, we'll catch, a bunch of airplanes, or near, where there are a lot of birds. We need that data. Because, as we also heard earlier today, you can't use AI and machine learning techniques with garbage in, garbage out. You need control data for training, because that way you know what's not anomalous. You know what a balloon looks like. So you can say with confidence, no, that's not a balloon, that's not a seagull, because you know exactly what those things look like in those instruments. So our philosophy is to try eventually to develop platforms that are on purpose deployed both in hotspots and in what you call cold spots, where no one's seen a UFO in 100 years. That's perfect, because that's your control data. We also want to do corroboration of anomalies, and you'll see some of this today with using public sources of data. That includes things like Doppler weather radar data, satellite imagery, if you can get your hands on it, and other types of globally available open source data networks, so that you're not only relying on your own sensors, but you can also try to corroborate any anomalies you find with all the existing sensor networks that all kinds of entities are already deploying around the country and around the world. So our initial instrumentation was visible light imagery using the UFO-DAP system, infrared, the combination of night vision as well as FLIR, and I'm going to talk about some of the software image processing we've developed. Radiation detection, we saw in Josh's presentation the history of claims of radiation sickness and physical harm That's really hard. How are you going to fake radiation sickness like a video? That's really, really hard, okay? And so that is going to, again, reduce the probability that you have a false positive and something that's not really anomalous. In the future, we want to look at going on the opposite of infrared. There's been a lot of focus on infrared. We also want to look at ultraviolet. We haven't had the time to even test it, but we have, collecting dust, unfortunately. We do have a camera system that's been used to photograph lightning in slow motion in the ultraviolet. That should be amazing for UAP studies. But that's under future technologies because we haven't even had the time to start calibrating and deploying these systems. But these are our eventual goals. We want to have, of course, electromagnetic field detection for obvious reasons with UAP electromagnetic field claims, piezoelectric, sound, strange sounds, infrasound, ultrasound, lack of sound. Things came up in Josh's presentation. And passive radar. So we've been collaborating with Gene Graniker. This is one of our biggest updates from our last presentation of 2 years ago that Kevin and I gave together at this very spot, at this very podium. So Gene saw me and also saw Rich and saw some of us on The Proof Is Out There on the History Channel. I don't think Miguel is still here from History. I think he had to leave, unfortunately. But the idea here is to use existing signals and have receivers that use existing signals from HD TV stations as the transmitter and look at the Doppler shift as your target crosses the baseline between the transmitter and the receiver and look for anomalous signals that are supersonic or hypersonic. And Gene is not too far from here, depending, if we're talking, light years, miles, what's our calibration for what's close and far, but he's in Atlanta. And he is working very hard in developing a reliable hardware and software system to be able to pull things out. And he has examples of data finding meteors and finding airplanes. He hasn't found any anomalous signals yet, but we're working with him for a potential future addition of passive radar to everything else I listed. So back to the past, though, what did we do for our first expedition? So if you saw our talk from 2 years ago, you're familiar with a lot of this, but there are also lots of new people in the audience or people who haven't seen the talk that Kevin and I gave 2 years ago. So we're going to go over our original findings. And for maybe not the first time, but one of the first times at this conference or this type of conference, we are retreading old ground because we have new conclusions on old information. So we have a Dahua 50232 camera that's the heart of the system, that is the heart of the UFODAP system. It's not a CCD, it's a CMOS chip that's going to be important later on. And we had the main unit we had deployed was on a roof in Laguna Beach, California. And we had a sensor package also, and that's one of the things I'll talk about later about lessons learned. We couldn't talk to the sensor package. It didn't record any of that data. All these beautiful things like magnetometer and ADS-B, so we only have the images from them. So the bottom left is an example of a daytime image in the camera of the Catalina Channel. The location, if you're not familiar, was chosen because of it's near the 2004 Nimitz encounter, and it's also a supposed hotspot going back before that encounter as well as afterwards. And the bottom right is an image here at the same perspective at 4 a.m. And this is our most famous ambiguity or potential anomaly that, of course, I'll spend several slides on later, where we saw a strange dark spot in this camera system. So here's a basic night vision example. And this is also an example of one of the updates from 2 years ago. And I was worried that Mick West would beat us to it and realize this, but he didn't. Because again, as I said a few slides ago, we're not even treated as important or of consequence. We're not even important enough to spend time debunking, which I don't know if that's a good thing or a bad thing. But we managed to figure out what one of our detections were that I spoke about with Kevin 2 years ago. We saw this fuzzy spheroid. We saw it in two night vision, says night vision goggles, and we saw that one of the cameramen in the movie saw it as well. Figured out that it was the International Space Station. And this was not trivial because the original website we used did not account for daylight savings time. As a result, my hatred of daylight savings time probably doubled. I don't care which one we pick, by the way. Just pick something and never change it again, for the love of God. Yes, thank you. Look, I've got small children. Do you think their bodies care that we change it doesn't make any sense. But as a result of daylight savings time, we almost missed this because it looked like the ISS was there an hour later. And I'm like, that's really suspicious. The direction matches, the position matches, the minute matches, but the hour doesn't. So I could have just said, well, I guess it's not the ISS. But I didn't. We didn't, because as like Kevin said earlier when he played the video with Penn and Teller, I forget which one is which. It was either Penn or Teller, the one that talks, right? I forget which one's which. That's a great example of not considering all the hypotheses. Who would have considered the hypothesis that the website didn't account for daylight savings? It was just some random website I found. The official ISS one I found did do it correctly, but it was tough to find. I was able to find a website that did give the right answer, and I have the link in the paper and on the slide, and it shows the historical data of wherever the ISS has been. This is an excellent example because this is not like satellites or airplanes. There's only one. And so this is a great example of something that it's a rare phenomenon, but still a mundane one. It's a human-made craft. So I mentioned earlier that we have an image analysis program. This is something I spent several months writing, where we were able to find, I have the math on the slide, but I'm not going to get into the nitty-gritty details, especially in the interest of time here. But we have developed a ridiculously simple system. It's not a magical AI, machine learning, any of that. It's a completely transparent analytic technique that all it does is subtract one frame from the frame before it. It's a simple, stupid idea. But by doing so, we discovered that in an RGB image, at least from the FLIR cameras we were using, we were able to find that there was a difference in the variance of the R, G, and B values between camera noise and actual objects. I'm not saying actual UFOs, I'm just saying anything, plane, bird, that allowed us to create a neural network-like separation. This is not a neural network, but we were able to create something like this graph on the right, where we have signal and noise. And again, the noise just means camera noise, just pixel glitches. It doesn't mean bird and plane, etc. Mundane craft are still counted as positive signal in the blue. So I mentioned also earlier radiation detection. So I'm now going into detail on all the different instruments we had. We have documented UAP encounters that involve apparent harm as a result of ionizing radiation. How are you going to fake that type of injury? I'm not saying it's impossible. It's nearly impossible. It's not as easy as coming up with a photo or video. And we have all these cases. There's Cash Landrum. There's the Rendlesham Forest incident, very famous since we had Senator John McCain arguing for disability benefits for veteran John Burroughs. Okay, and when I was a kid, Rendlesham Forest did the Unsolved Mysteries episode with Robert Stack. That scared the hell out of me when I was a kid, with a red orb in the forest. But you see how, even though on UAPx it's part of our mission we do not analyze old data. SCU, other organizations already do that. But we don't pretend that the decades of history aren't there. We use that history to motivate, well, what type of sensor platforms make the most sense to deploy? And so we use one of these very simple, cheap radiation detectors called the Cosmic Watch, developed at MIT. It's not meant for anything like this. I think the original makers would be, the stigma and taboo are very much alive. They'd think I've left the reservation for using it in this way. It's used for detection of natural cosmic radiation, but it's also a good general purpose radiation detector. So if you Google it, and I always get this question, why are you detecting cosmic ray muons from UAP? What's the connection? And my answer is, there isn't. You don't understand. This is a general radiation detector. It detects alpha, beta, gamma, neutron. Just because it has one purpose doesn't mean you can't repurpose it. It detects anything. And trust me, because we've calibrated it with hundreds of hours of calibrations of artificial radioactive sources. So it's not just it's a detector of anything. So it's very nice and general purpose. As far as we know, no known craft produce measurable quantities of ionizing radiation at a distance. But because we have natural radiation all around us, just like, so every sensor will have a drawback. It's not really a drawback, but you need calibration data. You need to know what your background noise is. So you don't just plug this in and go, oh my God, it's lighting up. Because it will all the time. It lights up 1 to 2 times per second. So what you're looking for is an anomalous extra amount of energy or rate or both above background. It's just like with cameras. You see an object, it could be a plane, a bird, or a drone. This also has a background that you have to look above. What's the average background counts and energies? So what were the lessons learned? We need more than one camera system. And we need greater redundancy in software. We need greater redundancy in battery backup. We also need to track more than just aircraft. We need to look at where are the satellites, where are the rockets. There are apps for that. Where's the ISS, right? Because we almost fell for that, because we need more than just the transponders. We need to know where's Starlink, where are all the different human craft at a given moment. We need to have multiple identical cameras, and they all have to have battery backups. Having many FLIR cameras was not as beneficial as was originally anticipated, because we generated terabytes of data that were challenging to analyze. But that actually turned into a positive, because that motivated us to develop software, so that instead of looking through 600 hours, you only had to look through 20, 30 minutes where something crossed one of the screens. We also need to make sure all our connectors are RF shielded against stray noise that can create camera glitches that might look like a UFO or UAP. We also need to synchronize all our clocks. So you think lessons learned would be at the end of my talk, but it's on purpose here because this is so important, and we don't want to run out of time and say, these are all the things we're going to do better. And device positions, of course, need to be recorded as well. So our most famous capture was on the UFODAP camera system and featured in the film A Tear in the Sky. I have a YouTube video link where you can see the original talk that Kevin and I gave 2 years ago. Also, that was even longer, where we dug into this. But I'm going to give the high-level summary for people who are not familiar with the original talk and our original results. So during our expedition, and this was not caught in real time, we only figured this out weeks later looking at the data. But we found a series, more than one, a series of strange videos. And I'm not going to have time to go through each one. That's why I have the YouTube link, and I have some still shots from them. But all the videos, you can see them all being played at that YouTube link, which takes you to the SCU channel, where our original talk from 2 years ago is. So we had at 3:50, the story really starts at 3:14 a.m. This is on July 16th, 2021, where this is a blank video in time without any obvious trigger in the camera. Then at 3:57:16, a diffuse dark spot appears at the upper right in the camera, showed you a preview of that at the very beginning of my talk. Its appearance may have triggered the UFO dap. It has no well-defined edges. At 3:57:27, the spot remains, the camera slews chasing an insect separate from it. Now, during rotation, white spots appear that turn into black streaks emanating from that spot. The spot is not visible in the later frames. So 3:59:24, cameras again stationary, darts are visible, and though the spot vanishes, a new white dot appears in a certain frame, and then at 4:13 a.m. we're back to just random trigger on an insect. So those are the words. Here are the actual pictures that go with those words. So you see this dark spot appears in the camera system, okay? And it appears, as I summarized on the last slide, in multiple videos. And again, if you want all the gory detail, got the YouTube link on my last slide that takes you to our 2-hour talk from 2022. But this is the high-level summary now of what we saw. We saw what looks like a dark spot. You know, is it in the sky? Is it in the clouds, or is it something on the camera lens, or is it in the camera itself? And what's really interesting is that in one of the videos, there are white dots within it that don't appear until the camera starts to move. And the camera moves for a good reason. It triggers on, there's something that looks like, you know, an insect lit from lights below that just crosses. So there's no mystery in one of the videos what triggers it. But then there's a follow-up video where you just have the dark spot with the white points in it. So in this is all of the frames. It was a short video, so, you know, less than a second. These are all frames of the 3:59:24 a.m. video. The temporal progression is left to right, then down, with 0.05 seconds, so 50 milliseconds in between, because the camera was operating at 20 frames per second. Now, so one of the lessons we learned is the disadvantage of an uncalibrated triggered system is there are no images immediately preceding and succeeding these frames. So we don't know. We have the earlier video from minutes earlier, but we don't know what happens in between those minutes, between when you have a dark spot with no white dots and now you have a dark spot with white dots. So in the future, we're going to do something similar to what I've done as a student, and I've done with different types of physics experiments, which is, you know, you can't record everything either, because you fill up terabytes and terabytes of disks of mostly nothing. But you can have a rotating buffer on camera systems that when there's a trigger goes back in time, some number of frames that it has stored in the buffer before those frames are deleted. So there's no time travel involved, but there's RAM. And you have cameras with built-in RAM or solid state on the camera itself. And so there's a way where you can have the best of both worlds. So we want to work with Ron and people with other who are making who have different systems and different software and hardware. And the optimal solution is to find something that's going to have some pre-trigger and post-trigger frames as well. So that's the plan for the future. But this is what we have, and this is our famous few frames where we have we have multiple videos, as I said, but our most famous video featured in our documentary film is one where you have this dark spot, and over time the spot fades and these white dots stay. And so this is a clearer version where I think this is actually better than me, you know, struggling to play the video for you here live. Is these are all, by the way, figures in our publication, in our scientific publication that's still undergoing peer review. And you can see here frames 1 through 16, and you can see in our #1 most famous video the evolution of the dark spot fades away, the white dots stay, and then a new white dot appears between frames 12 and 13, and at the same in the same frame as this extra white dot appears in the middle of the existing cluster, then a black dot appears in the upper right. You know, what is that? So the behavior of our dots are in some ways similar to the historical data, transients discovered by Dr. Beatriz Villarreal, who works on, she leads the VASCO and ExoProbe project. We'll be hearing from her tomorrow morning. But she's focused on historical photos and, you know, pre-Sputnik and pre-space age, for example, and things like that. But this looks qualitatively similar. You know, dots are there and then they're not. So here's one of the analyses we did, this was done by Kevin, was a pixel intensity behavior correlation. Because one possible explanation here is, you know, this was at 4 a.m., the camera was in near infrared, night vision mode. It's not a FLIR camera, it's a visible light camera. But what if this was, there was just pixel adjustment as dawn was approaching and the sky was lightening, but we can actually see that most of the pixels the change in pixel intensity is correlated in that area on the upper right. There are some pixels highlighted, and this is a false color map where deeper blue means there's a correlation there. You can see, though, that there are also some pixels correlated across in other parts. Now, we came up with 10. It's impossible to be comprehensive when you're proving a negative, and this is always the problem we have in UAP studies. But we tried to come up with prosaic hypotheses to test. We call these our null hypotheses, and there's 10 of them. That doesn't mean there can't be an 11th and a 12th, and some of these, as you'll see, to make it a nice 10, there's two similar ones we lop together. Number 1, false streak hole from aircraft, where the white dots are the aircraft, maybe a drone swarm or something, or camera noise, or it's a natural cloud formation. This one is really problematic, as we covered 2 years ago, because we don't have, in the records of aircraft in the area, we don't have, aircraft in that area, and we also don't have the right temperature, we don't have the right atmospheric conditions for a false streak hole. Another possibility is that this is a star field. Okay, this was the LA area. We did the math I'm pretty sure we did some simple math in the paper, but I mean, you don't need to do math to know that's not stars. This is the LA area, okay? It's not Montana, right? You're not going to see that many, stars. So it's not a star field, but we did the math, and it's like laughably off. The stars are in the wrong configuration for that part of the sky, and also it's too dense if those are supposed to be stars, it's too dense of a star field for this area with a huge amount of light pollution. Then this always comes up, and the know-it-all YouTube commenter goes, it's a water drop, evaporating. Ha ha, I solved it. Well, we did some math, and turns out no. That's unless you put 188 watts of heat suddenly on it. How do you have a water drop evaporating a fraction of a second? We did the math. Okay, it's a very silly, knee-jerk, kind of like debunker reaction. It's not a water drop. Now, number 4. Turns out is still in the running. It does not fit all of the data, but a fly on the dome leaving, and then the spot is suddenly gone. This doesn't fit all the data, because then it still doesn't explain what the white dots are. Okay, maybe they're camera noise, and we'll get into that later. So 4 does have some possibility. Number 5, the dots were created by radiation. After all, we discovered actually this event. I forgot to mention that earlier by looking at the radiation data, where it looked like there might be something unusual, and that clued us in to find this video in the first place. However, ionizing radiation is not going to be focused by a camera. And so we have examples, and we've taken data that I'll show you later. Radiation illuminates all parts of the camera image randomly, not just one spot. Then we've got meteor breaking up or meteor shower. There was no reports of a meteor or bolide at the time. Camera noise in the dark environment. That's possible. That would explain the white dots, but not the dark spot. Resetting of camera levels. We tested number 8 already. Number 9, everyone always says, it's a black ops military test. There's nothing we can do, unfortunately, to prove or disprove that, because, what are you going to do? Classify information. So number 9, we cannot do due diligence in trying to address that one. And number 10 is reflection of lights in the camera dome from the nearby city or cities. So if we look at the geometry, though, assuming that this is a physical hole in the sky, then Kevin did the trigonometry, and we're not claiming that, okay, it was a physical hole in the sky, but if it was some sort of atmospheric phenomenon, how far away was it? How big was it? We have to estimate, of course, because unfortunately, even though our ideal was multiple cameras, we fell short of that goal in our first expedition. So we don't have another camera, so we can't triangulate, but we can look up where the cloud cover was and see, okay, if it was at the cloud cover, if we take that distance out of the equation as an unknown and say assume that this was a hole at the cloud cover, then we can proceed and make this diagram. We can also, as you see here at the upper right, we can test the idea of whether this is camera noise. Camera noise should be what's called a Poissonian in nature, which means that the mean and the variance of the pixel intensities should be approximately equal. And we see that for cases of noise. We do not see that for cases that are actual objects. We did 3 control cases, and the white dots do not fit the pattern. So the case A are the white dots do not fit the pattern from what you would expect from noise. They have the same ratio of the first row number to the second as examples of objects in the camera, like a gull caught. So we wanted to also seek corroborative data to help go through these hypotheses. And so we had, actually, I mentioned him earlier, he's in the audience here. Matt Phelan helped us out and contacted, he's a journalist, but he contacted meteorologists to help us out to interpret the radar data. And we found something that got us initially extremely excited, that looked like it was at the right time and the right distance, that is identifiable as clutter. What's clutter mean, right? Okay, it's not precipitation. It was not, raining at the time. But we did our due diligence, and if you change settings, you find that, well, maybe this wasn't that anomalous, because if you lower the detection threshold, you see there are a bunch of these things that could be sensor echoes, like Peter was talking about earlier. So we don't have a smoking gun here that says, the radar shows that, yes, there was something weird. But I have to emphasize that, to the best of my knowledge, that this is the first time that publicly available Doppler weather radar data has been used in this way, and we're attempting to put this into a scientific publication. Radar has been used before, and we've had, Robert Powell got radar for the Stevensville case and things like that. We saw the FAA radar earlier today from Peter, but this is Doppler weather radar data that we didn't have to FOIA, that we didn't have to ask anybody, that we just got off a website. And now we're trying to use that in UAP studies. We really think that we hope that people will follow this example. Because how can somebody, they'll still say this, but how can somebody tell you imagine something, or, your camera had a glitch. Really? At the same time the radar detected something in the same location? So even though this time what we have is ambiguous, can't point to this dot here, we're very tempted to be like, oh yeah, we got it. But when you change the settings in the data set, it looks like it might be part of just background noise. So it's gray area, just like the image itself gray. We cannot definitively say it's something out of the ordinary. In fact, we went even deeper on the analysis. Matt did with colleagues, not me, but Matt Phelan, we dug deeper into this and did a scientific study where you have control data. Looked at summer and winter, look at different years, and you could have hits like we did. So we cannot definitively say. We've got seasons, we've got years where there are more random radar hits in the Doppler weather radar data that are classified as clutter and not as precipitation. So back to the ISS, following the same process we did there, we want to apply skepticism to our own results. And we used basic trigonometry to demonstrate that the object caught in the night vision goggles, recorded actually through night vision goggles, very, Corbell style, with iPhone and stuff, but it was good. It was good video. And unfortunately, it was probably the ISS. We can never say anything. Science is not mathematics. We don't prove anything with 100% certainty, but we can be pretty damn certain this was the ISS. Everything matches. There's the size, the speed. We calculated the speed, we calculated the size, and we could do that even though we didn't have triangulation, because just like we did earlier with Kevin's diagram of the hole, what we did is we said, let's take the ansatz assumption that this is at the altitude of the ISS and say, if this object is at that altitude, what is its size and speed? And lo and behold, it matches. And even though it's simple trigonometry, we put this in the paper because we want to show, but you can do this. We can all do this and determine whether objects are large things, far away, or small things in front of your camera, and be able to do the opposite and use the same basic math when something is truly anomalous to show that it is. And it doesn't have to be perfect. There are error bars here. There are uncertainties, but it matches the ISS within uncertainties. So that was in the night vision. Then we had the FLIR, which is a different wavelength of infrared. And we have in our scientific paper that I showed at the very beginning, we have a montage. And I'm really proud of this. Not just the 9 months of work, but I was also really proud of arranging it into a 3x3 figure to fit on the PDF page. So these are, because then I couldn't get a 10th example, because oh no, that'll mess things up. I'll make it an inset of this one. But we have all these examples that I don't have time to get into, but that we covered 2 years ago. We have examples of what's called a bolometric discharge, an example of what's probably an international flight into or out of LAX. We have a pair of airplanes, so it's labeled A, B, C, D, E, F, G, and then on the right, you see our most likely explanation for it. We've got the moon in D. E is a drone, pretty close by drone. That was that was the film crew drone filming us. F is still unknown. This is a strange collection, but it's a collection of dark pixels. We still don't know what that is, but we have very little data to be able to draw conclusions out of it. And G, this is really important because we thought, that these are hypersonic objects dropping into the ocean. No, it turns out it's something called an NUC, a non-uniformity correction in the FLIR. And are we embarrassed by that? No, we're proud. We own our mistakes because we don't let Mick West or Metabunk take care of things for us. We clean our own house at UAPx, and we look critically at our own data so that when we present something, we labeled it 2 years ago as preliminary because we didn't know, and now we actually are starting to have some conclusions. We got this nice parasailer, also someone enjoying themselves off the coast. We caught that person from several different angles, and that's great because then we can test our triangulation capability. Same thing, we got a helicopter in H, so that's great. We can test our skills then at being able to reconstruct these objects. In the future, though, we've got a new miniature FLIR. I brought it 2 years ago, actually, and I took a picture of the crowd. They said no, pictures. I know FLIR counts, so you can't tell people. But a couple years ago, I'm sure it's still on Hoover, is I took a picture of everybody on the new miniature FLIR, which is miniature, but it's decades more up to date than what we had before. But we have only one of these. We want to obviously get more because one of anything is not enough. But we wanted to show off how beautiful, you've got a crescent moon and how beautiful an airplane looks. It doesn't look like a Tic Tac or cigar, so you're not going to mistake a human aircraft. I mentioned earlier how we were recording radiation. We made tables of what could be potentially anomalous both in rate as well as in energy in our Cosmic Watch detector. We looked at the energy spectrum and we found several potential candidates that didn't follow the trend of lower rates of radiation at higher energies, which is just, I don't have time to get into the physics of that, is just a standard well-known trend. But when we looked at the statistics, I don't have time to get into the math, but we could apply statistics because of the calibrations we did at the Cosmic Watch, and we were able to figure out that seeing one of the high energy events that was very famous that we talked about 2 years ago and is in the movie, there was a 20% chance of seeing something at the 40 MeV famous energy. So we can't declare it's anomalous, but there are many other what are called systematic uncertainties to consider, where if we consider certain things like, well, are the other videos in time? Is that video cluster statistically improbable? And so it's ambiguous depending on how because as came up in Q&A for Kevin's talk today, there's still, even if you try to be mathematically rigorous with statistics, there's still the human element of what probabilities you assign a priority to certain classes of events. So depending on how we do this, this event is, so it's on the borderline, statistically speaking, as to whether it's anomalous that we saw some mysterious dark spot in the camera at about the same time as we got a radiation detector. And this is tricky because we're constantly bombarded by natural radiation. So the conclusions from our paper were that in light of all the possibilities, our most intriguing event is ambiguous. And but we conclude our paper by suggesting some very stringent conventions and adopting what's used in particle physics, the so-called 5 sigma standard, where something is classified as an anomaly only if it has a 1.35 million chance of being a statistical fluke. And that sounds pretty ironclad, but even this still requires interpretation, because you still need to know, well, what null hypothesis are you comparing to? So most of UAPx's ambiguous observations ended up being identifiable, but we concluded so many things that we think are going to be helpful to everyone. We recommend at least 2 of each type of sensor, and we'd love to be able to do new excursions, both to Catalina for reproducibility and elsewhere. So I have a whole bunch of thank yous, but they're in the paper. But I also have a few extra slides that I'm not going to spend very much time on because I'm coming up on the hour here. Actually, Rich, can you tell me, do I have until, is it 7 or 7:15? What's the official time that I have? Because I think since I'm using my own computer, I don't have the countdown.
Well, I mean, we got down here questions and answers at 7:10.
Questions and answers 7:10, perfect. All right, so I will be done at 7:10, perfect. Okay, so I summarized up to this point things that many of you have already seen 2 years ago with updates. The non-uniformity correction for the FLIR and the our best hypotheses for the dark spot. We had updates, but there's more. This conference is about bridging the gap. How do we bridge the gap between government, academia, and science? Well, I've got some ideas. Well, we need to get published in academic journals. We're working on this at UAPx. Our paper's currently under peer review. This is not going to be easy because you still have stigma, but we have to try. We also have to get our preprints up on the archive server. This is hard. I have colleagues, some of this in this room on Whova, who got rejected days after I succeeded, and I was very disheartened by that and thinking, wow, extremely lucky then. How do we continue to bridge the gap? We need more PhD or other advanced degrees like DSS, like Josh scientists, as well as engineers. They have a different terminal degree most of the time than PhDs. We need funding sources. I think one thing we need to do is to try to consolidate some of the existing organizations and also consolidate a lot of the resources. And also, this is not a dig against Rich. This is constructive criticism. Scientists should be allowed to finish their slides in the last minute. So Kevin and I are always giving Rich trouble. He always wants the slides 2 weeks in advance. I'm like, that's not how scientists work. My record is, and this is normal. This is not out of the ordinary. My record was 15 seconds before I'm about to get up and give a talk. When I was a postdoc, I finished the slides. That's just how it is, and because we're so busy. So beyond the first paper, we have new results I'm going to show you now in the last 10 minutes. The UFODAP, the system exposed to radiation, water, heat, light, darkness, and fly analogs. What was our fly analog? Well, Ben Kugelski and I, we literally printed a fly on a piece of paper, and I cut it out and he put it on the camera. And many new papers are being planned that I'm going to talk to you about in the next 10 minutes. So, but first, I've got to do this. This won't come out, I think, on YouTube till December. Something new that happened when I wrote an essay. It was originally on Medium, Common Criticisms Against Studying UAP. Oh, and Metabunk went to town on it. And one of the things they said was, me personally, I have almost religious faith in the potential of technology. And they went on to talk about how special relativity prevents interstellar travel. If you're going to tell a physics professor they don't know physics, you should get your equations right. So, I'm really hoping that when they see this, I'm not holding my breath for this, is, I've come up here and we have on UAPx, we've courageously admitted our mistakes. We didn't find a wormhole, probably not. We didn't see a glowing orb. It was the ISS. I'd like this Ann K, he blithely assumes engineering can do it, and this Mendel, so it's not Mick West. Are they going to have the guts to apologize to me? We'll see. I'm not holding my breath. So they describe energy as mv squared. I'll forgive them for forgetting the 1/2. However, that's Newtonian kinetic energy. And I love the part that says Einstein for dummies. Really, then why did you use Newton? Who's the dummy here? It's not me. And so then to help Metabunk and to help Mick West's cronies, I put the correct equations there for them, hopefully help them out. But you know what the greatest irony is? The correct equations actually make their point stronger. I mean, how stupid is that? So actually, yes, they're right, interstellar travel is hard. Oh, you mean like air travel, that thing the New York Times said was impossible? In the famous article saying flying machines will never fly. It will take millions of years for humans to develop. Oh, and 2 weeks later, Wilbur and Orville Wright. Or the New York Times editorial against space travel. We're here in the Rocket City Tavern. They were making fun of Werner von Braun and saying how, space travel, there's nothing to push against. Atomic bomb. I don't remember who said this. Kevin will know who said this. Someone said to President, I don't know if it was Truman or Roosevelt, atomic bomb will never work. And I speak as an expert in explosives. So gotta love these experts in relativity on metabunk.org who don't even use the correct equations. So, and one of them, I can't find it, so maybe Mick took it down or a moderator. On the same thread, somebody literally wrote, I couldn't find it, otherwise I'd have a screenshot, so I couldn't find it again. Someone wrote, Szydagis' knowledge of physics is poor. Okay, you don't say that to a physics professor. And so, how about using the correct equations for interstellar travel? So I'm going to wait and see what happens when they see this, if they see this talk. I'd love to see them back their way out of this, Einstein for dummies, and then using the Newtonian equation that doesn't work in relativity, and they forgot the 1/2 for that. So actually 1/2 mv squared is the Taylor expansion. I wonder if they know what that means over at metabunk.org. It's called the Taylor expansion of the correct equation. So to be fair, it's not Mick West himself. I've got a pretty positive relationship with him. I think he does legitimately want to find the truth, but this is not him. This is one of the random people on his website. So in the interest of time, I'm going to fast forward a few slides to wrap up here and say, okay, we did what Mick West does in his garage. We tried to mock up what we saw. And we found something that's pretty similar. Actually, most of the credit on this goes to Ben Kugelski on our UAPx team. So Ben and I did try to replicate our dark spot. We had a fly analog. This is in a dark room where we tricked the camera into night vision mode, and then we just blew off our fly analog. It looks pretty similar. But one thing that's interesting is that the dots still don't match the expectation you would mathematically for Poissonian noise. And then we figured it out. The CMOS sensor has different types of artifacts than the CCD that most of us are used to. So now our best educated guess, our best hypothesis is we probably had a fly on the lens and it took off and it left a camera artifact unique to this type of camera sensor. So that's our best guess right now. We looked at light, water, we looked at more fly analogs, and we looked at a water droplet placed on the camera, and we tried to slew the camera. And again, the water droplet, though, it disappeared too quickly for that. So I'll show you, though, the water droplet test if it loads. And you can see this is by Ben Kugelski. And you can see the water droplet right there. You can see it in the upper right. He tried to mimic the same location. And it seems to have some of the similar at least qualitatively, a lot of the similar features. There you go. See right there, you see it's not exactly the same, but you see white dots, you see black dots. It's similar enough that we think something like this, not a water droplet in particular because it disappeared too quickly, but something similar like a fly taking off may be the explanation. So we did also another fly analog test. So this is, again, Ben blowing something off of the lens to try to replicate the same effect. And you see all kinds of artifacts from the software and from the CMOS sensor. So there he's placing his fly analog, out in the country, beautiful dark sky. So a lot of these are really similar. So we might have some sort of dynamic scaling behavior of the camera, and we may have a prosaic explanation for this. But we had some fun with this. We kept going. Even though we thought we had an explanation, we started testing radiation. So this thing here that looks like the eye of Sauron, that's my Californium-252 source. Very dangerous, no joke. Like, you have to be a real scientist or engineer to be qualified to handle something this dangerous. And so we used it safely. Ben and I were far away behind shielding, but we created this really cool, we've got this really cool graph that shows there are more glitches, more little pixels like this you see here that appear, and it appears to scale with the amount of radiation. That's really cool. We don't think that's ever been done before. For CCD, yes, but not for CMOS. We don't think anything's been published. This is pretty publishable. I think this is pretty cool. But this doesn't explain the white dots because it's random. It's random because a camera cannot focus ionizing radiation. Speaking of particles, though, this is one of the bombshells I have to drop in my last 10 minutes, but I've got proof for you, like proof with a capital P, that working on UFOs is not a waste of time. Because of working on this topic, I was inspired to create a new type of nuclear reactor I was inspired to do it because I heard about Robert Salas. I read UFOs and Nukes, and I'm like, can I make something that is a safe, modular nuclear reactor? Turns out it is possible. So I have all these, that's a whole 1 hour talk on itself. So I just drop in the seed there. I'm not gonna talk about it again until I have a paper published, but the videos are only for participants, are not gonna appear until December from this. And I'm hoping to have a paper because there are so many claims of solving the energy crisis and stuff. I'm not talking about it again until we have a scientific paper. But I had to toe the line because also I need money. So you gotta get investors interested. So I have an article in the local paper, Times Union, and a very over-sensationalized article in the New York Post, which got me in trouble. And so as a result, I'm mentioning it only very briefly today, and Kevin brought it up during his Soul Foundation talk to sell this. But I want to stick this, just like the earlier slide, stick this to the Uber debunkers, that we made a real discovery that has nothing to do with UFOs by being inspired by looking at this. So it's irrelevant. I believe this is all real. I think a lot of what Ross said last night is plausible. But even if it's not, if there's no conspiracy, there's no reverse engineering, and there's no non-human intelligence, I don't believe that. But even let's say for a moment that's true. Discoveries are being made just by thinking about these possibilities. And that's very important. Another thing, and this is again evidence that I don't think we're all crazy. Something that I'm working on, I have some help. I got a lot of help from Robert Powell, who use NLP, natural language processing, and I got a huge amount of help from the Kalamazoo UFO group. We have people from there here. Okay, I'm not going to show the graph because again I'm running out of time here, but I found a pattern in UFO colors that hadn't been noticed for 80 years that matches one of the exotic hypotheses. I'm double and triple and quadruple checking this, but trying to turn this into a real scientific publication when the time is ready. But if this is true, this just adds to what Josh said earlier. if it's hallucination, how did tens of thousands of witnesses all conspire over 8 decades to produce the same pattern of colors? It makes no sense at all. So Eric Davis, who kind of helped inspire me with that color idea, also inspired another idea, which was also, of course, inspired by Grush's testimony. He attended SU in person 2 years ago. Nobody knew who he was. And I didn't believe until Gary, showed me photos. So yeah, it's Gary's fault. You can't take photos, right? He's like, hey, look, there's Grush at the table behind. And I'm like, I didn't know who he was. Who was that guy? And lo and behold, he's like, there, Grush was sitting at the table behind you, Matt. And I'm like, holy cow. Well, this whole thing about crash retrievals, I have to say that I was always skeptical. I really want to believe that what Ross told us last night is correct, but we've got to get the facts. So I thought of doing a little calculation, and I'm going to, again, these are all long-term plans because this is unfortunately a hobby for me and Kevin and our colleagues like Cecilia, Ben. We're not paid to do this. But I like to calculate, okay, let's assume that all these stories of crashes are correct, and I want to determine mathematically what's the rate per century, per decade. And I'm going to calculate the rate and the probability of what was called at Soul Foundation as chaotic disclosure. Or maybe it was catastrophic. I may have messed that up. It was C disclosure, chaotic or catastrophic, and I'll be corrected later. And the YouTube commenters, catastrophic? All right, so my slide is wrong, and all the YouTube commenters will yell at me. I apologize. I just misremembered. I wasn't there. It was secondhand. Eyewitness testimony. Anyway, just kidding. So catastrophic disclosure. I'm going to calculate the probability. Because if crash retrievals are real, and again, I'm on the fence on this. If they are, it's only a matter of time before it happens in the middle of Times Square. The Earth is big. It's not that big. It's not the size of Jupiter, right? If crashes are that common, then eventually it happens in the middle of Times Square, and good luck stuffing that genie back in the bottle when it's 12 people, 12, 15, 20 people have it on their iPhones. And I'm gonna actually do this calculation. And NASA has software for this, also deorbiting. I'm gonna look at the existing calculations for NASA has software for calculating, what are the odds that, Skylab was gonna crush your house or something by accident. But these are the things we're working on. Also, so testing of materials, this ties into the whole crash retrieval thing. How do you determine whether something is not human-made? Well, this is not a surefire way by any means, because there could be other options that cause this, but isotopic analysis is a big deal. So one thing we've been pioneering, it's not a new technique, but we're pioneering how to do it cheaper at UAlbany, is something called neutron activation analysis. So chemists, material scientists will probably be familiar with this. This is a non-destructive method for determining what something is made of. And we use the same cosmic watch for this that we use for our in-the-field detection. What you do is you use a radioactive source like the californium I mentioned earlier. You make something radioactive temporarily, very low, very safe amount, very briefly, and you look at the half-lives. We have already used this technique. Again, it's not a new technique, but we've already used this at University of Albany to find less than 1 part per million impurities, because that's how sensitive this technique is you can find individual tiny trace amounts of atoms. So this is a great technique. Someone says you've got some crash parts, and we've already done this where Kevin and I took some alleged crash material. Turns out that the atoms in it corresponded to human-made aircraft of the time. As again, great control data. Not as exciting as saying, oh my God, it's interstellar craft, but it's a start. It's a start. So crashes would definitely be more plausible, but the Earth is findable. So Kevin's working on a paper, and I'm also going to work on a paper with him and others, where I'm going to I'm talking to Beatriz, to Dr. Villarreal I mentioned earlier, and experts on this, so that I don't make a mistake, because I'm not a member of the SETI community or field. I want to talk to people about what's already been done. Kevin, as I said, is already writing several papers on this, given several talks. But I want to take the idea of simulation of civilizations to the next level. I don't want to be limited by the speed of light. I'm going to look at the work of Eric Davis, Travis Taylor, Bobrick and Mateer, Heisenberg, no relation, but I'm uncertain. Lenz, I don't know if she's related, Lavinia Heisenberg. So there are all these professors. You know, a lot of people obviously were bored at home in 2020, and there was a whole flurry of warp drive papers. So I want to look at these exotic possibilities. And Kevin already has done looking at the sublight possibilities of spread of civilization over time. And together we want to conquer all these different hypotheses for what potential civilizations could be doing. And then Kevin is also working on multiple papers to put into the scientific literature some of the extreme accelerations, extreme speeds, luminosities, and electric fields. And he's looking at, we've got, McCampbell, 1983, Mark Roediger, his work from 1981. And lastly, but not least, we need to find time for a publication on the CTAP software I wrote for detection, for motion detection. So I'm going to wrap up now because we're heading, I'm up for my time. So in conclusion, I think we're going to continue to look for UAPs, but quality science takes time and it can't be rushed. We're moving slowly, carefully, scientifically, and most importantly, boringly. So that's from John Oliver, a quote from John Oliver, where I'm not dazzling you here with a wormhole or a UFO that is definitely anomalous, but we are trying to do things carefully and move the ball slowly down the field. So field expeditions are worthwhile is one of our important conclusions. Even if you find nothing, most of our results seem to be null results. The dark spot is still ambiguous, but it looks like we didn't find anything, but we gained experience. In my own day job field of dark matter research, this happens all the time. Look at this New York Times article, dark matter experiment has detected nothing, researchers proudly say. And we proudly say also we detected nothing, but we've come up with suggestions of basically, to quote or paraphrase Josh, of a curation standard based on statistics. So it ties in to similar equations that Kevin was showing himself. So I'm happy to answer any questions, and I'll end with a shameless plug to please take my class on the physics of exotic propulsion that's being run by Mike Sifone of Society for UAP Studies, another UFO organization. So I'll leave this quote up there. The great advances in science usually result from new tools rather than new doctrines. Freeman Dyson. Thank you.